side, there is an option where the student has to choose one of the subject. And you see, these topics, I mean, these are like typical like list of topics. It is nice. I mean, you see there are very variety of the things, measurements, mechanics, thermal physics, and base, and like so on and so forth. But then these things also brings a problem. And the problem is that these topics seems very, very independent and indifferent to each other. And the students really struggle to find out the connection or how to connect them. I mean, the students find them that it's like a vast sea, and they get lost in them easily. And it's very, very difficult for them to concentrate, and that's the reason the students who choose physics is very, very less. Like very less students choose physics in their optional science subject. So, and of course, like the topic seems very, very different. Like there's a measurement, then there's a circular motion, and particle physics, and nuclear physics, and of course, it seems that they are different. So there should be a way to make them to connect them, like to connect all these topics. There must be a way. And of course, then in the next two slides, I'm going to present to you how to make physics easy and maybe fun. What are the possible ways to make physics easy and fun, and how to connect those seemingly different topics. Okay, so I got two different ideas I'm going to share with you, and of course I would be very much willing to ask your opinion about this and to improve myself. The first thing is, you see that these are very complicated things. I mean, maybe most of you have realized this is particle trajectories, and there's a fine Feynman diagram. So the physics becomes very complicated if you just go a bit, if you go deeper into any debate. In order to simplify this thing, we need to find a pattern in any of the topics. The pattern we can find out from the symmetry. So the physical things, I mean, once we are teaching them or once we are learning it, we need to find out the symmetry or the correlation, or if there is a repetition, or if something is repeating itself, like a sine wave, it's a repetition of the same values. And interestingly, if you think this way, most of the things comes out to be very, very similar to each other. For example, like the trajectories of particles, there's a particle zoo, there's hundreds of particles that are discovered inside the nucleus. So in order to categorize them and study them, we need to use the symmetry and then the other things. And of course, also all the laws of conservation they are based on a symmetry of a physical things. So like the pattern is very important. We need to find out the pattern in the physical phenomena. Okay, and once we find the pattern, the very next thing is to connect them. So this, I think in my opinion, these two things, the pattern and then the connection is very important. Like once you find out the pattern, you have to connect different things. The connection could be correlation and proportion, like how they are related or how they are dependent on each other. And there are a list of, I just came up with this 4 in the last hour. But of course, there are many more connections. For example, Apple fall and celestial motion. This is what Newton described. The force with which the Apple falls to the ground is the same force with which the moon rotates around the sun. So there's a connection. It seems very different motion, like the fall of something, and the heavenly bodies they are revolving or rotating around the center. They are seemingly different, but they are the same thing. And of course, if you just go a bit more deeper, you will see that all the motion, they are essentially circular, and then they are somehow connected. They have the same pattern. Electricity and magnetism, I don't need to describe this. Acceleration and gravity. These things very, very, very different things, right? Acceleration has nothing to do with gravity. But of course, if you read the relativity theory of Einstein, you'll see that they are the same thing. So you see that even though they are different things, but once we approach the subject from this angle, everything becomes so connected, so beautiful, that you also love it, and then everyone loves it, because we want the connection, we want some pattern, which is what we like. Mass and energy, they are different, but E equals mc squared. And of course, we can add much more things. Think of any two different seemingly different things, and then you find a pattern. This would also be a nice activity. Sometimes we do this in our class. We ask our students to find out two different things, like force and maybe pressure. I mean, we know that there's a connection, but of course, whatever they find out, they realize that they are connected somehow. And this is actually very amazing. So these two things are, in my opinion, are a backbone of teaching or learning or teaching physics with fun or with easiness. So the first is pattern and then connection. Okay, so with this we can make physics fun, and if these are a reminder, the F in physics stands for fun, and if you ask if there's no F in physics, then that's the point. Okay. There's a nice quotation, I don't know who said this, but I just remember this and then I wrote it down here. So if you love what you do, then you'll never have to work a day in your life. Like many people, even myself, I want to get a day off from my school because the students don't listen to me and so many chaos and problems. But if you love what you do, then basically you're not working, you are just having fun. Like imagine we like watching a movie, or at least I like watching a movie, and I don't feel that I'm doing something because I like it. Similarly, if I like teaching physics, then it means we are not working. We are just getting money, salary, without doing nothing. So, for free. Okay, so there are a couple of things. In the next 3 slides, I'm going to share with you some resources which I found helpful and interesting. So I just want to also to share it with you. Yes. The first one is SPET. I think most of you already know it, but I want you to realize that if you log in, if you sign up in FET, you like with your instructor email, you find a number of worksheets and the prepared assignments. So you can just take a printout and then you can give it out to the students, and then answers are also available. So it's a great resource, and please use it. Sometimes you feel that if we just give these things to the students and if you don't teach them, then it won't be good for us. But I think it is better if you, I found it helpful that if I don't teach them, if I just give them some assignment and then if they discover the pattern or the connection themselves, it's more engaging. This is one of the things. The second thing is the physics with video analysis. I just started doing this a couple of months ago, and I found it very amazing, and mainly because it's so versatile. You can do so many different variety of experiments. It's very engaging. The students usually just give out the worksheet, and the students spend. We have a 1.5 hour lecture, so the students spend like the full time without asking me that when the lesson is going to end and doing something. So they focus and they find, and you see that. And then with video analysis, you can do so many variety of the things. But in the next couple of slides, I'm going to show you what you can do with these things. And then this is also extremely low cost. Of course, for video analysis, we use many different softwares. Like one which like yesterday we have seen is the MATLAB, which is of course expensive and it's also heavy. So for even myself, I can't buy it. It's so expensive for me. What I use is Logger Pro. It's a very lightweight software and it's also very cheap. I think it's just 100 or so. I think $50 or so. It's very cheap. And I also have a CD of it, which is licensed. I think we can share, I guess, or maybe. So once we have this software, then the worksheets for all this video analysis are also available. And I'm going to show you the worksheet and the manuals in a while. But then there is also a very nice website for the tasks and everything. So in this website, if you go to this website, you will find out many nice videos with the worksheet and with the answers, and some of them they are really amazing. You also, maybe I'm not sure about the students, but when I started working on it, I started liking physics and these things. So worksheets and manuals. Logger Pro also provide you a list of worksheets and manuals. They are also freely available, especially the student version. But I have bought the instructor version, and here you see there are 33 different experiments, or not experiments, the video analysis you can do. For example, This is Snell's law. You can just verify the Snell's law, and there's a nice student version. The worksheet, for example, you can see. The students have to read this, and then they will be answering some of the questions here. And they are very self-explanatory. They can, once they read and they do some research, they find out the answers, and they understand even much more than you when you explain in a lecture wise. So once you give them this worksheet, for example, I think they would learn, they would understand much more than when I explain them, I guess. And all these, by the way, like the solution for these things is also available. So you don't have to spend extra time for yourself and then finding out the correct answer or something. So the same worksheet is also available. And this is also like a Word document, so it means you can also add them. You can, according to your own criteria or whatever. But of course, there are many resources available online. This is one of them. Sorry. Okay. How much time?
2-3 minutes.
Okay. So the last thing is the Kahoot. Maybe some of you know, but this is something which I really want you to experience. I can explain this. I mean, this is one of the things the students love it. This is some. They even request me to use this one in the classroom. So I think it's a good idea if I don't explain it to you guys, if I don't explain it what it is, but instead if I let you experience this thing. So I hope you all have internet on your mobile phone or your devices. No. Yeah. So it will take only 2 to 3 minutes. Do you have internet? If not, then maybe you can share with the one who have it. I think it's a nice idea to experience because this will give you something in your heart when it starts pumping. You will see it yourself. Okay, so we started. By the way, this is the thing which the logger code looks like. Oh. So I mean, you can check the things and then it plots the graph automatically, and then you can do some simple things. And it's more visual. You can play with it. It's not, you don't have to code the thing. So it's rather simple and straightforward, and it only takes 5 to 10 minutes to learn this software. So it's not the learning curve is very simple. Okay, so I think let's play this one. So please get ready with your devices, mobile phone or internet. You can also use these computers. So I want you to go to kahoot.it, write this on your browser, Chrome or whatever, Safari, whatever, kahoot.it, and then put these numbers there. Someone missing? Do you have access?
I don't have right now.
You want to do this? Okay, just log into this. Okay, should we start? Okay. So you're going to see questions here, and then you have to answer on your. You have to answer on your mobile, but the questions are here. Just
यहाँ से यहाँ
So you have to read the question here, and then you have to answer on your devices. But of course, this is just to, it's not to test you, but just to, for you to see.
I just clicked and then I saw oh my god. ये एंड पे डिस्प्ले भी होना चाहिए फिर
Can you make your own questions?
Sorry?
Can you make our own questions?
Yeah, this quiz. Some of the question I made myself. That's it. If you find a question which is wrong, which is not right or not looking good, but there are millions of prepared images available on the web. You just have to go in and log in and find out. There are literally millions of ready-made questions available. So please use it. You see, like you feel something in your heart, like when you play. Same, your students also feel this same thing. And even if they're sleeping or whatever, this makes them awake and everyone is involved. So I would just definitely recommend you to use this in your classes.
कोई मिस हो जाए तो रिव्यू हो सकता है
Sorry?
मिस if we miss something then can repeat
Once. Okay, of course, and then you can also pause and then you can also explain like why this is not true or false, and then you can also see how the students are thinking, because you know, like I can see majority of the people, they are right. So I don't think I need to spend some time here, but if you see the students are making mistakes, you can pause and you can also explain the thing, and then you can also know how they are thinking and how which level are they at. Which of the following things use the random error? we have like 4 more questions, but this is going to be last one, I guess. Given the time. Okay. Okay, so let me skip. So I mean, we have 4 more questions left, but like at the end of the quiz or game, you can see the list of the students who like the top 5 students, and this makes them happy, or and then you can also get their feedback on this thing. You can also replay them with their host. So there are many other options. So once you go into this one, you will find out yourself. But I think you have realized that how inspirational this thing is. So I will now try to manage it. Okay, thank you very much, and yeah. Should I go any further questions?
You have a comment.
Yes, please.
Can I?
Yes.
I would like to thank Hassan for the interactive talk, and especially for reminding us of the connectivity, to connect subject and physics together. I think that many students and also even teachers, they miss this point, the connectivity. If you teach a course in quantum mechanics and involve in one question something depends on Newton's second law, students will get stuck because they are guided to think in one direction. They are not guided to connect physics topics together. So I think we need to highlight the idea of connectivity.
Asad Hussain is physics undergrad, student of Dr. Shiv. He would be presenting a talk on video microscopy.
The last talk.
Having to last.
Hello guys. My talk will be nowhere near as interactive and colorful as the last one, but I'll try my best. It's a slightly technical topic, but the idea is basically that you have. Oh, sorry, just a second, guys. But well, the basic idea of video microscopy is that we take a video of lots of colloids in a solvent. Colloids are basically little particles that move around in a larger solvent, and you look at how they jiggle, and then you cover statistics about them, and then you try and guess what type of particle that was, right? So that was the basic aim when we were doing this experiment. And yeah, so video microscopy, sorry, I'll just repeat. Video microscopy is that you take a video of little colloids in a solvent and you see how they move around, right? You analyze the videos, collect data about how the jiggling of the molecules happen, and if the jiggling is of the Brownian motion type, you know statistically what should happen, right? So using that, you can calculate different things about the particle, its radius, its mass, etc. So basically, Brownian motion is a thing called a continuous time and continuous state stochastic process. But basically, all we need to know is that Brownian motion is a type of motion where if you look at how the square of the coordinates vary. So if you have, for example, the particle started in a particular position, right? And after a while, you look at how much it's separated, right? Now, if you look at the average squared separation from the particle from its initial position, it should follow this relation, right? It should be proportional to time. So if that's true, then you can use that to calculate D, right? And D has this nice relation where K is the Boltzmann constant, T is the temperature, eta is the viscosity of the solvent it's in, and A is the radius. And most of these things, temperature, the viscosity, and Boltzmann constant, you know that. But A is something that you can figure out, right, by looking at the video. So if you have a weird liquid in which you don't know how big the particles are, and you want to measure that, this is a nice way to measure the radius of a particle inside that's jiggling inside some water, let's say. Okay, so that's the general aim. You know statistical properties of Brownian motion, you can use that, compare that to a square, right? But there are two methods, right? One is simple, the other one is slightly complicated. So we started with the simple one and then we moved on to complicated one. Right. One is called video particle tracking, which is what you think it's going to be. You take the images, right? And I'll just show you a sample image. Yeah. See, that's a sample image. So this is one image of a bunch of colloids in water, right? So what we do is this is a video, but this is just the first image. After a while, one particle moves to the right a bit, this one moves to the left, yada yada. This is just slight jiggling going on, right? Now what you do is, in video particle tracking, what you do is the algorithm detects each of these particles. It says, oh, this is one particle, this is one particle, this is one particle. And it's pretty cool how the algorithm does it, but I'm not going to go into that. But it just, say, circles each of the particles. For the next frame in the video, it then circles them again. And then it looks at how the motion happened, right? Now that it has the paths of each of the particles in this solution, it can now look at the statistics about it. So all we did basically was to say, okay, fine, you have all of those motions, and now just average the square displacement from the initial position for each of them, right? And just plot that against time, and that should be a straight line. And we did it, and that's what we got, right? We got a straight line, and using the gradient of that line, as from here, yeah. From here, we know it should be 2D, right? In the case of, it was basically in it's basically in a two-dimensional plane. It was exhibiting Brownian motion, so it's actually 4D, right? So we used that and got the Boltzmann constant and Avogadro's number, which is sort of close, I think 20-30% error, right? So that was video particle tracking. That was the relatively easy bit. So there's this other kind of way to track particles. It's called differential dynamic microscopy, which is slightly harder, and it involves one particular result about Brownian motion, which has to do with this thing called the autocorrelation function, right? What you do is it's just if you don't know about the autocorrelation function, it doesn't matter. It's just something that you can calculate for a video, and some guy has sat and calculated this for Brownian motion, right? And the result is that it should come out. This. It should be a decaying graph, right? So e to the minus dq squared. Okay. Now how do we calculate that? What we do is we've got lots of images, right? At different times. So this is basically a video. What you do is you take the differences. So for a particular delta t, right? You say, okay, fine, I want to try to find the video difference at 3-second difference. So what you do is you start with a particular image, then you look at the frame 3 seconds later. You subtract those frames, right? Then you Fourier transform them, right? Now what you do is you keep on taking those differences and averaging that around with time. What happens is in the end you get this average spectrum for given delta t, right? And what should happen is that the autocorrelation function should follow this, right? Where q squared is this distance, right? In Fourier space, right? It's very abstract. It doesn't seem like exactly that's what you're going to do. But what happens is that you can use that. This is the result we got. So this is from if you put two frames, 1.17 seconds apart, difference, then fine, and average them out and Fourier transform them, then this is what you would get, and we got that, right? And so we did a lot of analysis and tried to get the autocorrelation function, right? And we got it, right? And it should follow something like this, right? And this is q on this axis, and this is delta t. And you can see it's sort of decaying. Right? You have a decay, and the decay goes closer and closer and steeper as it goes up. And this is another one, right? This is the same graph, but it's nicer because it's done in a color gradient sort of way. But we did this, and we should have gotten the same results as the video particle tracking. But there was a slight problem, right? When we did dynamic differential microscopy, we assumed one thing. We assumed that we can get these coefficients out, right? So there's this analysis that we have to do to get the autocorrelation. This is the autocorrelation to figure out, right? And this is some constant function of q that we have to find, and we add another constant function of q, so just so we can just for noise, right? Just to make sure that the noise terms can be accounted for. So once we have that, we need to sort of fit these, right? Find which functions we can sort of fit our data onto. But in doing that, one way is to say, okay, oh, you have your autocorrelation function, and when delta t is really small, this is about 1. So this goes to 0, and you can use that to find dq. But when this goes to infinity, you can use that to find aq plus bq, and then there you go, you have both your functions. But that sort of fails when you have very low frame rates. When you have low frame rates, you cannot say, oh, delta t goes to 0, because you don't have that frame where delta t is actually equal to 0, 0.001. The smallest delta t you can get is actually 1 over the frame rate that you have, right? So that sort of fails. So we did this analysis, and we have slightly wrong answers, right? But I am in the process of developing a method by which we can sort of fit these without having low frame rates, and sort of fit AQ and DQ without having to do that same analysis of delta t going to infinity or 0, which is the normal method to do it, right? In the paper where they first did dynamic differential microscopy, they had frame rates of 400 frames per second, so their analysis was pretty okay. When we did the experiment, we had 9 frames per second, so that didn't work out that well, right? But for some colloids which might move really slowly, 9 frames per second might be awesome. It might work. But for colloids which we had, which were 5 micrometers across, that didn't work out. Well, so yeah, that's basically why it didn't work out. But experimental science is such a thing. You never know what's going to happen. This is what happens in research. You try it and you fail. You go, okay, fine. Let's think of a better way. And I came up with 3 different new ways to work on something, and ended up that they didn't work out. So far, it seems like I've done nothing, but in fact, I've worked a lot, and I've actually learned a lot on this. Because by doing these experiments, and Sir Sabi lets us do whatever he gives us, you have to do this. Here's this method for analyzing a video.